In this lecture, we're going to go through a demonstration, an example of how to compute something called the standard deviation. And so when we think about the standard deviation, as well as variance, we'll get to that as well, always begin with the term deviation. And that's exactly what we're doing on this slide here. So what we have here are some sample scores obtained from a research study from participants. Participant 1 had a measurement score of 3. Participant 2 had a 4, 7, 9, and 10. The first step is to add up all of the participant scores and place that value as a summation in the immediate cell below the final participant score. Then in the next cell, we calculate the average by summing up all the scores and dividing it by the sample size, in this case, which is 5. That gives us an average of 6.6. In the next column, we calculate the deviation of each participant's score. And so the approach we take here is we just follow the formula. So we take the raw score, which is a 3, we subtract it, we subtract the average of 6.6, and we get negative 3.6, and we keep the negative sign. And we repeat that with a 4, subtract 6.6, 7, subtract 6.6, and we do so on and so forth with each participant score. And then we add up all of the deviation scores, and we find that all the deviation scores will sum to 0. And if we wish to gain an idea of how much these scores varied around the average, this would not be very helpful. So the fix to this zero-sum problem is to calculate something called the variance. And the variance, we basically just square the deviations. And so with each deviation term, so for participant number 1, we have their raw score, subtract the average. We then square that value because if the deviation score comes up as a negative value, squaring it will eliminate that negative value. And so then we then average the squared deviations around the mean. So what we do here is we take each squared deviation term for each participant, and once again we have our sigma symbol here, so we're going to add up all of those terms and divide by the sample size, and our example is 5, and this is something called the variance. So working through this example here on the slide, here we see, just as a repeat, our deviation, the problem with the deviation summing to 0. But now we take the negative 3.6, we square this term, so negative 3.6 times negative 3.6 gives us 12.96, negative 2.6 times negative 2.6 gives us 6.76, so on and so forth. We now add up all of these values and we get a final value of 38.64. And then we take that 38.64, which we have up here in the numerator, we divide it by the sample size. In this case, we have a sample size of 5, and we end up with a value of 7.73. And this value is the average squared deviations around the mean. And this is what we call the variance. Now, the larger the sample variance, the more spread out the scores are around the mean. Now, calculation of the variance carries some potential problems. The variance measure produces very large values. No value actually deviates from the mean by the calculated value. So if we go to the table here and we see that we have a score of 3 for participant 1, we see that the score of 3 deviates from the average by 3.6 in the negative direction. However, the squared value is 12.96. The same goes for participant number 2. Not as big a deal for participant number 3, and we see that pattern continue. So from the previous example calculation, we have a variance of 7.73, but if we take a look at the actual deviation, how much each score deviated from the average, no one score deviated by this amount. So that's certain, so the large value here doesn't so far it does not reflect the fact that it's going to be representative of how much each participant score deviated from the average. The second problem is that the calculated variance units actually do not make sense. Let's suppose we were measuring participant age. We know that the units for age is years, but when we go through and we calculate 3 years subtract 6.6 years, we get negative 3.6 years. But when we square that term, we not only multiply the number by itself, we also multiply the units by itself. And so the units in the far right-hand column and the units for the 7.73, if this was a measure of age, would be years squared. So this makes no sense in terms of our research question. So is there a way to fix those problems fix the two problems observed with the sample variance? So recall the squaring the terms solved our first problem of having a zero sum to the deviation score. So that problem was solved. But now we have the other two problems. Well, the simple solution to this is to take that squared value in the opposite direction mathematically, and that's to take the square root. So whenever we have this operation, the square root symbol and the square value here cancel each other out. So we're just left with s about x. And so this is our formula for the sample standard deviation, which is going to be the unit of measurement or the unit of variability to which all of the subsequent statistics are based upon. And so this now becomes a measure of what the average deviations around the mean for all of the participants. So because all the participants deviated by a different amount, we need one number to provide us with an idea of how spread out those scores are. So from the previous data, we calculated the sample variance, and if this was a measurement of age, this would be 7.73 years squared. But when we take the square root of 7.73 years squared, okay, I've got an 8 here, so that was a typo here. But when we take the square root of the numerical value and we take the square root of the units, we end up with 2.78 years. So the sample standard deviation now carries the units as the original participant score. Making note of the typo here, 7.73 and 7.78, the 8 should be a 3 here. This ends our video on the calculation for the standard deviation.